Hey, in this video, I'm going to walk you through a missing data analysis in SPSS, and then imputing missing values using multiple imputation. Uh, my syntax file and the data sets I'm going to use in this video can be found on Canvas. We're going to use a couple data sets from the high school and beyond survey from the U.S. Department of Education. And the survey basically asked students, it was like a general assessment test. And asked students, what type of program they're in high school, whether they're on like a general academic or vocational track. And it also gave them general assessments on their writing ability, reading ability, science achievement, those kinds of things. You can Google more about the assessment if you want. So I have on Canvas here two data sets. The HSB2 data set has complete data for all 200 cases. And then the HSB2 underscore MAR is a data set where some data have been set missing at random. And so then we're going to use this data set to then impute to run our missing data analysis and multiple imputation on. So first thing we're going to do is I'm just going to open the data set with missing values, run frequencies on all the variables just to confirm that there are missing values. So you can see here, everybody has something for ID, 18 people are missing for gender, both race, socioeconomic status, school type. I have complete data for everybody. The type of program people are in is missing for 18 students. 9 people are missing reading scores, 17 are missing writing scores, and you can see that. Okay, so if we were going to run an OLS regression, regressing reading scores on students' writing scores, their gender, their math scores, and the type of academic program they're in. We first have to dummy code the academic program. So I'm going to create 2 dummy variables, one representing a general track, one representing an academic track. And so we're basically going to be then comparing general track to vocational, and do as an academic track to vocational track. So that's basically what this does here. We can 41 students were in general, 95 were in academic. We just want to make sure that our dummy variables have 41 and 95 in there, and 18 are still missing. Here would be our regression analysis with missing data. You can see 70 people were dropped from the analysis because the regression is going to require people to have valid scores on every variable in the model. So you have to have a reading score, a writing score, a score for your, an indication of your gender, a math score, and then what academic program you were in. If you're missing on any one of those, you're dropped from the analysis. So we'll come back here. We'll compare in the assignment. On there, have you compare these results with the full case results and then with the multiple regression results. But in this video, I really just want to run through the the missing value analysis and multiple imputation. Before we run our missing values analysis, it's a good idea. It's good practice just to make sure all your variables have the correct level. So female, SES, maybe we could argue is technically ordinal, school type, academic program would all be nominal scale variables. And then our test scores for writing, math, science, and social studies would be continuous, or what SPSS calls scale. We could just check these in the, we could go and check on the variable view tab and make sure they have the right right measurement level, or we could just, you know, force a change. If, you know, they're already set to the right level, it's not going to change anything. So either one doesn't matter. Our missing values analysis, SPSS, I think does a really good job of this. Is the MVA command, missing values analysis command. You tell it the number of variables. I mean, you know, what variables you want to perform the missing analysis on. And I'm just including every variable in the data set, even if it's not going to be in our regression model. You can tell it, which variables are categorical. You tell it you want separate variance t-test for any data that, you know, for any variable that's missing at least 5% or more of cases. Same thing for your categorical variables. You can tell it if you want crosstabs for those variables. You can get the missing data patterns that are in the analysis, and then an estimate of the maximum likelihood estimated descriptive statistics, so like means and standard deviations. So we run this syntax, see it printed up here at the top. First thing we get from here is just some basic descriptive statistics. So we can see there were 191 valid cases for reading. There's the mean, the standard deviation. 9 individuals were missing a reading score, and that represented about 4.5% of the sample. It also gives you an indication of outliers. You can see here in the footnotes, it's defining an outlier as 1.5 times the interquartile range. So it's saying that, you know, none of them seem to be like extreme cases. It's just kind of flagging that for you. Anything that you declare that was categorical, it's not going to calculate a mean and standard deviation. It's going to give you the percent that's missing. So, you know, 18 people are missing the gender variable, about 9% of the, so you can see each case, you know, has between roughly, you know, 5 and 9% missing. Some have no missing data, like everybody has a social studies score. Everybody has an indication of their race or ethnicity here. But remember, when we ran the regression analysis, it ended up dropping 70 people, because if you're missing on reading, if you have a valid case on reading, writing, math, but are missing on female, it's going to drop you out of the analysis here. Here's just a comparison of the this should be the observed means. Okay, 52.29, and these would be a maximum likelihood estimated means based on the expectation maximization algorithm. You can usually compare these to see how maybe how close they correspond. Same thing for the standard deviations. This is the part that's really cool, the separate variance t-test. So basically what this is doing is taking the writing variable, whatever variable's on your rows here. So it's taking writing and it's dichotomizing it. So it's creating just an indicator variable that has a 1 if you have a valid writing score and 0 if you're missing on writing. And then it's using that indicator then as an independent variable to predict variation in these outcomes. So here we're saying, you know, whether you are whether you're missing or you're not missing your writing score, you know, do you have, you know, is that related to your reading score, your math score, your science score, or your social studies score? And you can see here it computes, here's the mean reading score if you have a writing score. Here's the mean reading score if you're missing on writing. And so it's a t-test between these two means. And so here we can see our p-value. So we can see that missingness on writing doesn't seem to be related to any of these other variables. We could look down here for missingness on math. It looks like we find a small p-value here for math, a decent size t-statistic. So this is saying that missingness on math is related to students' social studies scores. And we can look here at the means, and we can see that those who are missing a math score tend to have lower social studies scores than those who have a math score. So there's a relationship there. It'd be nice if it also calculated like a Cohen's d effect size here. And then we could really see the larger the effect size, the stronger this relationship would be, and the better predictor, we could say, social study scores would be of missingness on math. But we can kind of use the size of the t-value to sort of judge that. In this case, a test statistic like the t-value is basically an effect size that is convoluted with the sample size. And so to calculate the effect size, we usually take that sample size out. Here they all roughly have the same sample size, so there kind of is sort of a comparison we could use there. Well, we basically follow the same procedure with each one of these row variables. So for science, we could look and we could say like missingness on science scores seems to be related to reading scores, math scores, and social studies scores. We could look at the means and we can see that, those who are missing on science, those who are missing their science scores tend to have higher reading scores than those who have science scores, who have scores on science. Same thing for math. Those who are missing science scores tend to have higher math scores than those who have a science score. Same thing for social studies. Those who are missing their science score tend to have higher social studies scores than those who have a science score. Here we're not really here we're really only interested in, like, we're using these for like purely predictive purposes. We want to be able to predict what this missing value might be, not necessarily then understanding the relationship as to why those who are missing on science scores tend to have higher social studies scores. Really mainly interested in whether there is a relationship and then the size of that relationship. Same thing here for female. It looks like, what are these? Writing and math scores do a good job of predicting missingness on the gender variable. It looks like those who have a valid gender case tend to score higher on both writing and math than those who are missing, than those 18 people who are missing their gender score, or not a score, but an indicator for what their gender is. For academic program, it looks like none of these variables do a good job of indicating what type of program students are in. So for your categorical indicator variables, so for like female academic program, it gives you a cross tab. Here we would kind of compare the different, the means, or not the means, the proportion, I guess they're technically means, variables. But anyway, the proportions across to see, you know, where we see drastically different proportions between males and females. And notice we see for the math scores, we see, you know, pretty different proportions between males and females in their math scores. Same thing, we could look at those who are missing on math versus whether they were male or female. You know, missing and the total be another indication. So, you know, we would just kind of go through here and look at all of these and kind of make a judgment call. They don't give you, you could actually compute like chi-square test for these to get a p-value and effect size. But you'd have to do that by hand. We could see, you know, here we can see if race is a good predictor of missingness on any one of these variables. Same thing with SES and school type and academic program, you know, are any of these variables good predictors of that. You could also compute like just like a correlation matrix between the variables to kind of look at you know, how interrelated some of the variables are. You know, typically I've seen like rules of thumb, if it's correlation is greater than 4, that might be a good or a decent predictor variable to include in the imputation model. You know, when you're thinking about what variables to include in your imputation model, you should include at a minimum all the variables that you're going to include in your analysis model. So remember our regression model up here, we want to include at a minimum reading scores, writing scores, gender, math scores, and the academic program they're in. But we could also include what they call auxiliary variables, variables that aren't necessarily you know, of main interest in our main analysis, but might help improve predictions of missingness on some of our other variables. Like we noticed here, like social studies scores, remember, was a good predictor of missingness on math, and it was a good predictor of missingness on science scores. So we'd probably want to include that in our imputation model because it does a good job of explaining why people are missing on some of our variables of interest. So you'll typically see those are called, they call them auxiliary variables. We also get like a pattern. You know, this gives you a table of you know, the kind of like the pattern of missingness sort of cases. So there's 117 cases who that have complete data on every single one of these variables. If we, you know, what this is saying is if we exclude the academic program, there we have 131 cases who have complete data on all of these variables in the analysis. So you gain an additional 14 people. If we exclude gender, we would have 132 complete cases on all these other variables. So we'd include another 15. So this shows you the different patterns of missingness. Sometimes that's helpful in knowing kind of what's going on with the missing data that you have. So here's your different maximum likelihood estimates of your means, covariances, and correlations. The important part of this table is it gives you Little's missing completely at random test. So this is a chi-square test where the null hypothesis is that the data are missing completely at random. So this is one of those cases where we want to fail to reject the null hypothesis. So that would indicate that that would be, you know, a piece of evidence to indicate that the data are missing completely at random. Here, we reject this test. The test is statistically significant. So we would reject the hypothesis that the data are missing completely at random. So that means the data are probably either missing at random or missing not at random. And so we're trying to build then an argument here that the data are missing at random. We can predict some of the missingness with some of the other observed variables that we have in our data set. If Little's MCAR test here is not statistically significant, that doesn't mean the data are missing completely at random. It's just one piece of evidence to indicate maybe they are. But it's still, depending on how many cases you might drop, you still might think about maybe running an imputation model or something maybe to help keep that sample size that you have. So I think we built a pretty good case that the data are missing at random. We can predict missingness on a writing variable on our math variable from scores on social studies. We can predict missingness on science from scores on social studies, math, and reading. We can predict missingness in the gender variable on scores of writing and math. So I think we have a good argument here that the data are missing at random. So we're going to run then a multiple imputation on these data sets. If you look in the syntax file, I give you some syntax for running. The first thing we're going to run is a diagnostic check just to make sure that the imputation that we're requesting is running correctly and the imputation converges and nothing's going kind of wonky with it. So multiple imputation is a stochastic or a random process. So in order to get the same results every time, we need to set a random number seed or a pseudo-random number seed, or else every time we run this, we'd get something different. So if you want to get the same results I do, we're going to use this as our random number seed. And so this syntax here, the only thing you would change in this syntax are your variables right here, and then where you're saving out your file. You need to name whatever file you're saving out. You're going to change the path, but leave the name of the file as parameters.sav. You can change the file path to wherever you're going to save it on your computer. And then you could leave this part alone for our example, but if you're running this on your own data, you would add in your own variables here. So I got this from Ender's Applied Missing Data Analysis textbook. He created an SPSS macro that performed some diagnostic checks for us. So we can help to make sure that the algorithm that's running converges to a stable distribution, and it kind of help. We're only going to run 2 imputations here, so it gives us a chance to make sure that give us an idea of how long this is going to take to run, and gives us an idea if we get any errors, we can kind of solve them before we're actually trying to run the main imputation results. So we're going to run this like it is. It's going to output a file called parameters that we're then going to use to run some diagnostics on. So let me just run this. It'll take it a few seconds to run.